We're going to go over all of the labs because there are things from every single lab that you need to be able to perform well on the final. Okay? Let's think about lab 1, and maybe you might want to pull out your sheet or something like that, or if you remember lab 1, you remember it, that's good. What kinds of things are we going to need to be able to do from lab 1? All right, what do you think are the important components, important things that you learned in lab 1? Yeah?
How do you use a waveoak, micropipette?
Okay. Most of the stuff in lab 1 is so fundamental that it won't be stuff that you're specifically quizzed on, but without it you won't be able to achieve anything else, right? Okay, good. What about lab 2? Lab 2. What did we do in lab 2 that you think you might need to be able to do well moving forward in your life? Preparing solutions. That's right. And you will need to prepare a solution. So we don't have time to do everything in all of the labs in this, speaking of which, I forgot my computer, in this small 2-hour, or hopefully 1 to 1.5 hour block. So here's a couple of chairs right here. Anybody wants them? So, when we say you're going to have to know how to do whatever it is, for example, prepare a solution, you will have to know how to prepare a solution, but it might be that you only do one step in the process of preparing the solution so that it saves time. In the end, I'll be able to know if you can perform that task. That's just an example, okay? So, preparing a solution means what? What components? What do we need to know how to do to prepare a solution? If I want a 0.3 molar solution of copper sulfate, 250 milliliters, what kinds of things do I need to know how to do there? What's that? All right, dimensional analysis. I need to know how many grams of copper sulfate I need to put into that solution. Good. The calculations. What else do we need to know? Or what should we do when we're actually preparing the solution?
Putting in solute before adding all solvent.
Okay, very good. So making sure that we're filling to the volume with solution as opposed to with solvent as opposed to taking the solvent and adding the solute to it. Good. What else? Tell me something about the glassware. Is that a big deal? Where would that come back to cause problems for you if you didn't use the right glassware?
Accuracy?
Yes, that's right. If your solution or your unknowns that you're going to be determining aren't correct because you made incorrect solutions, then you'll lose points there, right? Okay, very good. What would be the appropriate device to make 0.3 molar, 250 milliliters of solution? Graduated cylinder would be okay, but what's the best thing for making solutions? What's that? Erlenmeyer flask would be less okay. What else? Volumetric flask. That's probably what you're thinking, right? The volumetric flask. Right? The volumetric flask has a thin neck such that the air associated with your location here will be very minimal compared to the actual volume change here. Does that make sense? So that's why the volumetric flask, and we'll hold this up for people at home, right? Volumetric flask is the best tool, the appropriate tool to make a solution. Do we want to run through a calculation, or do you guys think you got that?
Yes, let's do it.
Okay, we said a 0.3 molar solution, 250 milliliters, and I want copper sulfate. Okay? Go for it. Do it. Work that through with your neighbor. I'll be right back. Work that through with your neighbor. Did we get it? Yeah? Okay. What did we get? What's the value? 11.97? Anybody else get that? Anybody else want to make a different vote? No? Okay, so let's go through this. Okay? To the right of the equal sign goes what? Grams of? How do we know? Yeah. But what do we have to do to make sure that's what we're actually after? We have to look and see what they've provided us, correct? Because what are the options that they could have provided us?
Hydrate.
Yeah, some sort of hydrate, correct? Does that make a difference? Is that a big deal?
Yes.
It does, right? So, grams of copper sulfate hexahydrate. All right. And now we start off with wanting 0.3 moles for every 1 liter of solution, 0.25 liters of solution. Is that okay? Moles of copper sulfate. That's what I want. I don't want moles of copper sulfate hexahydrate. It's actually the same, but it doesn't, I mean, you know, the ratio is the same. But I want this, but this is what I have to weigh out. Correct? So then I have to go from moles of copper sulfate to moles of copper sulfate hexahydrate. Right? And then I can go from moles of copper sulfate hexahydrate to grams of hexahydrate. Right? Everybody okay with that? 0.3 times 0.25. What's this ratio here? 1 to 1. 1 to, what value did you guys use for this answer? Who was it that gave me over here? Yeah. What's that? Okay. So they use 159.67. You would use whatever the mass is associated with your copper sulfate hexahydrate, right? So if we do use that mass, do we get 11.97 here? So we got, who got it? We only have like 3 people that got it. Okay, lots of people got it. Great, excellent. Okay. Do you want to come up and sign your location for the, because you gave us the answer, you want to come up and sign we have a sign-up sheet here, right? So you get to choose your times, 8 o'clock, 9 o'clock, or 10 o'clock when you want to show up on the next Tuesday, right? Next Tuesday. Do you want to come sign up? All right. So just put your name into one of those slots. So we're going to come in waves like that, right? But it's just by invitation right now. So.
Oh.
What's that?
Are these all the same day?
Yes, it's all the same day. Okay, so lab 2. We need to make sure we can do the calculations. We need to make sure we can identify the glassware. We need to make sure that we know to put the solute in first, followed by the solution, or the solvent, right? What else do we need to know? There was one more thing there, I feel. We were using densities in chapter 2. Is that correct? Or sorry, lab 2. Did we take the density of our saltwater solutions? Remember, we put some copper sulfate. And we did that in lab 1 as well. Knowing how to find the density of a solution is critical. I think we did it enough times that everybody would have or be comfortable doing that. Okay? Identifying the density of 1 milliliter of water is critical for your future as a scientist, if that's what you plan to do, because in most chemical and biochemical or biological applications, you're going to be using a micropipette, right? And when I get a micropipette, I need to make sure that this thing actually works according to what it says it does here. And how do I find that out? Yeah. If I take a volume of water, put it on the balance should tell me the mass of the water, which is the density of the water, right? And so I can know whether that volume is correct. Okay? Is that important for you guys? Yes. If we went through all the micropipettes over there in the stockroom right now, we would find a percentage, maybe it's only 10%, but a percentage that are bad, right? That have errors in them. Okay? And if you use them in the lab or in your future research here as your undergraduate project or whatever it is you have to do, and you don't check it, then that's it, right? You can't rely on your data and you'll be running around in circles. Okay, good. Lab 3. Well, what did we do in lab 3? Okay, a spectrophotometer, right? We used the spectrophotometer to identify the relationship between the absorbance at a certain wavelength, right? Let me grab a solution here. I have this beautiful solution of copper sulfate. What wavelengths of electromagnetic energy are being absorbed by this copper sulfate solution? What wavelengths? Okay, red. What wavelength is that? What's our range of wavelengths that our eyes can see? 400 to 700, all right? You know, maybe somebody might argue a little bit further than 700, but generally it's 400 to 700. Okay? Which color is 400? Okay, so talk to your neighbors and come to a consensus. One person says violet, one person says red. What color is 400 nanometer light? Okay. Did you guys change your mind, or what did you decide?
She's right.
She's right. Okay, come on up. You get to sign up now. All right, so how are we going to remember that? How are we going to remember that? How did you remember that? What was your thought process? What's that?
Ultraviolet infrared.
Okay.
Ultraviolet is a higher energy, greater frequency, and then infrared doesn't have much energy, so it's less of a frequency.
All right. Ultraviolet is higher energy. Now, how did you know that? Just because. All right. Ultraviolet, higher energy. We know that because we know that. Grandpa taught us a long time ago or something, right? Cartoons, commercials, who knows. But ultraviolet, higher energy, higher frequency, right? 2 wavelengths of light or electromagnetic energy, right? Here they are. If they start right here, which one's going to finish first? Same time. So if they're moving at the same rate, then one of them has to be moving up and down more frequently, and that one has more energy. The more frequently it moves up and down, then the shorter the resulting wavelength. Right? The shorter the wavelength, the higher the energy. So, what color is 400 nanometer light? Violet. Purple. 700 nanometer, therefore, is what? Red. Okay, so we have a material here that is absorbing what color wavelength then? Or what wavelength of electromagnetic energy? 700. Around the 700 range. I can tell it's not absorbing, a little bit past, maybe in the 500 nanometer range, because I can see the blue. That wavelength is getting to my eyes. True? Okay. So, if I were to plot absorption of light versus wavelength, right, would the peak be on? So here we have our 400, 700. Would the peak be to the right or to the left here for this solution? I mean, we actually did it in lab. Did anybody remember where the peak was? What's that? 543? I thought we just said that this stuff was going to absorb the red side, right? So that should be down here. The cobalt had an absorbance of about 5 something. The copper sulfate had an absorbance where? It was actually way over here at 810, right? Remember that? No? Well, you can look through your lab reports and try to remember it or read through their labs a little bit. Okay, so why is it important to take the absorbance at the peak, which we call the lambda max? Lambda refers to what? Wavelength. Why is it important to take the peak at the lambda max, or the absorbance at its peak? Why is it important to identify the absorbance at that location? Is this location more sensitive to the amount of material that I've put in? The amount of material that's in the container, the cuvette? Okay. If I have a different concentration of this same material, it's been diluted now, right? Then I'm going to get a curve that looks something like that, right? And a lower concentration yet. What do I do with this set of curves after I have all these curves? Why would I gather all these? What would all these do for me? To find a relationship between what? What do we want to do? Concentration, different concentration versus what? Concentration of the copper sulfate in this case, right? That's right. The absorbance, concentration of copper sulfate, our units are molarity, and the absorbance at a given wavelength, right? Which we want to choose the max if we can, so that our relationship is the most sensitive. Okay? So, why do I apply a linear fit to this graph? Because we know that that's a relationship that exists. Absorbance equals concentration times the extinction coefficient and path length. And because our extinction coefficient is the same for the compound, the path length is the same, we can just drop those out and recognize that absorbance equals concentration. At dilute concentrations, right, you can't have too high a concentration, because once the concentration is high enough that all the light is absorbed, if you continue to get it higher and higher, you're not going to be able to get more absorbance if you've already absorbed all the light. All right? If I were to take the absorbance right here and plot it versus concentration, would that work? I would still get a linear relationship. The slope would be shallower. What's the ramification of using a shallower slope in a, what's this thing called? Standard curve. What's the relationship, or what's the ramification of using a shallower curve in a standard, shallower slope in a standard curve? Should I say it again, or do you got it?
Is it less accurate to the true value? It is precise.
Well, I guess I need to know why. Why would it be a problem? What's the ramification? Yeah.
It'd be a problem because, like, when we were saying earlier that ink is the most sensitive color. So if you're taking data from the that's not as sensitive, then your data isn't going to be exact.
Okay, so let's look at this. When I make 3 or 4 solutions of my unknown, I get a range of values. Like when you do anything 4 times in a row, you get a range of values, right? Maybe it's 0.83, 0.82, 0.81, 0.87. Does that make sense? I get a range. Get an average and a standard deviation, right? But the range, right, this now represents the range that I'm putting in. That range will propagate through to the values that you will calculate here. If the slope of this is relatively steep, then the propagation will not be significant. However, if this slope is shallower, this same, I should probably use a different color. If this slope is shallower here, this same error range will meet up with the curve at a different location. And you'll propagate a much larger error because of the lack of sensitivity. Can you see that? Okay, so that's why we use the lambda max. All right? What else did we learn? We learned how to use the spectrometer, right? If one of your lab partners said, hey, can't figure out how to use the spectrometer, what should I do? What would you tell them? At this point right now, how could you learn to use the spectrometer if you can't remember how to use this thing? Because your lab partner was so good, they did all the labs for you, or whatever. You didn't have an opportunity for whatever reason. If you don't know how to use this and you're feeling uncomfortable going into your final, what would you recommend to your lab partner? Or the person? What's that?
Yeah. I mean, my advice would be just to go through it a few times, but if you're asking in terms of steps, you just take 3 milliliters.
So go through it a couple times, meaning come into the lab and work on it? Okay, good. Very good. You can come sign up. That's a good answer. What other kinds of things could you do? Yeah. Okay, so that's an important component. You can come sign up. That's good. What else? Yeah. All right, very good advice. Come sign up. Watching the lab videos. Remember the lab videos are out there that describe, I think that was pretty heavily described. I don't know if anybody sat up and watched all those videos all night long, because there's a lot of them. But yeah, Anything else that you might be able to do? Yeah.
Maybe offer to help, like help you walk them through it.
Okay, you could walk them through it. If you don't have time, you don't need to. You could say, Dr. Scott will walk you through it, right? And after this, if you want to hang out and do something, anything, you're like, hey, I can't remember how to do this, then you can do that. You want to come sign up for us? All right, good. All those are good things to do. And that doesn't just apply to the use of the spectrometer. It applies to the use of anything technical, all right? We didn't use a lot of other things, instrumentation and stuff, but if you're having any concerns about Excel software, right? Making graphs, anything like that, then yeah. All those I think are pretty good answers. Downloading the software onto your own laptop could be a critical component as well. Okay? The software is called Logger Lite. Logger Lite. All right? Who said Logger Lite? Come on up. Come sign up. Logger Lite. The idea here is you're comfortable with it on your own computer. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 computers here. We have 12 spots signed up. We're not going to force anybody out. Okay? So let's say you sign up for 8 o'clock. You don't have a clue how to do this. You're thinking, I didn't do any of my labs well. I was just copying along the way. I don't know what I'm doing. We're all working on our own, right? So no lab partners to help us. But if I just stay there long enough, it might work. All right, great. Let's do it. Right? You come at 8. You leave at 12. Right? That's fine. Okay? So because of that, it's going to get crowded in here. All right? Some people will be here longer than an hour, and some people will be here longer than 3 hours. Right? So at 9 o'clock, if you come and it's your time, if there's not space for a computer, we'll find you some corner if we can. But if you're going to need a computer to use software like that or Excel, right, then that'll be another limiting factor. And you'll just have to wait for one to kind of free up. But if you have the software on your own computer, then nothing will limit you that way. Okay? Okay, so I think that is all the things that... Oh, we should talk about how we'd identify the concentration of an unknown after we got such a standard curve. Let's clear up our standard curve again. We should also have a talk about when we add y equals mx plus b on an equation. When we put a fit to it. I get scared when I see fits. I guess, did we ever have, I can't remember now if it was in this class or not. But, oh yeah, it was. Some people putting linear fits to this absorbance versus wavelength, right? What's the linear fit for? Is it just you do it, you always do it, right? That scares me to death, right? Anybody from, well, I don't need to take a toll. This is serious business. What is the #1 state in terms of snake oil? Do you guys know what snake oil is? Fake cures. Claims that this will heal you, this will make you happy, this will do wonderful things for you. People sell it for a generation and then it disappears because it did nothing. The #1 state, what is it? Utah. Utah. Okay? Is that a problem? That is a significant problem. That does not bode well for us as a people. Why is that the case? Because we think we can cash in spirituality for intelligence, miracles for understanding. It is not the reality of the law of the harvest. Okay? You can't, these are not exchangeable currencies. All right? So, do I care that you're mindlessly doing things? Yes, I do. So when we put a linear fit on something, we're only doing that because that equation actually means something to us. In this plot here, what does it mean to us? What does it mean to us? Huh?
Calculate
it allows us to relate. Did you get to sign up yet? You want to come sign up? It allows us to relate absorbance to concentration with an equation that will, the math will tell us how much of the given chemical that we're after, we want to know how much there is in our unknown. Okay? So, I have this plot now. I have my unknown. I put it into a cuvette, right? What do I do with that unknown now after I have it in my cuvette? Put it in the spectrophotometer. Then what? Take the absorbance value. Yeah, collect if you haven't pushed collect already. Take the absorbance value, and then what? Okay, this is an Excel and graphed already, right? And so then what are we going to do with that absorbance value? It goes into which axes, yeah. Which variable? To the y variable, right? We're getting our absorbance on the y-axis. And then we can solve for x, and that should tell us the concentration of our absorbance, right? A lot of people make this graph incorrectly on the final. All right, some people will go like this, absorbance versus concentration, and they'll get a plot, but they'll actually have plotted the concentration values over here and the absorption values over here, and they don't know it. Does that make sense? I've taught you how to make sure that you know which side is which, and if you have any concerns about that, then that's something you should want to make sure you either talk to me about or recognize, okay? Some people make this plot incorrect by plotting concentration versus absorbance over here. Okay? Is that this equation here, y equals mx plus b? I can put my cuvette in my unknown in the spectrophotometer, get a value, and then in this case, all I'd have to do is plug it into what? The x-axis, right? You plug it into the x-axis and then solve for y, the concentration. So some people do that, and that's fine, right? We haven't emphasized, what's it called? Independent variable, dependent variable, all right? And to me, it's a little, it's not very important. So you don't lose, you lose maybe 1 point if you do it like this. But you'll lose a lot of points if you say absorbance versus concentration and you actually switch the values, right? That's not a good sign. Okay, so I think we know how to identify a concentration of an unknown, right? And hopefully everybody knows how to make this graph in Excel. I think we've been told enough that we need to work in Excel. We can't work in Google Sheets, all right? Do not work in Google Sheets for the rest of your academic career, all right? The only time you work in Google Sheets is when you're at home with your kids and they say, I need to do this. Okay, here you go. Because then it's always there. It's always there. It's saved. Another way you can use Google Sheets is you take all your Excel data and paste it into it. Then it's always there. And then when you're ready to work on it, you copy it out and put it back into Excel, right? Unfortunately, it won't save any equations for you. But I've found that as a useful tool that way, okay? Google Sheets is the devil's tool to trick you into not getting quality data because they're not going to improve Google Sheets fast enough for it to catch up to Excel. And the quality of and the abilities of Google Sheets is minimal, okay? So don't get confused. All right, lab 4. Lab 4. What did we learn in lab 4? A titration. We did a titration. We determined the concentration of bicarbonate and carbonate in a solution. And I thought you guys did in a sample. I thought you guys, so far, what I've corrected, you guys did really well. Maybe I haven't corrected too many, but you guys have done really well. And so I was glad to see that. identifying concentrations given an unknown, right? Which basically boils down to calculations, is that right? So that's something you're going to need to know. All right? Do we want to run through a calculation, or we kind of make one up? Okay. So here I have a solution. It's my unknown. All right? It has A in it. Okay? I don't know the concentration of A. I need to know the concentration of A. All right? I'm going to perform a titration. I have here in my burette chemical B. I know the chemical reaction. 2 A's plus a B equals A2B. All right. In here, I put 10 milliliters of solution A, unknown solution A, and let's say 40 milliliters of water. My standard, what should be my standard here? If A is my unknown, then what? What's my standard? B. B. Did you get to sign up yet? No. So many people said B. I think you said it. You can come sign up too. So B is our standard. That means we have to what? Know the concentration. We have to know the concentration of B. So let's say we have 0.1 molar B. 0.1 molar B. All right. We perform the titration. It takes 18 milliliters of B. 18 milliliters of B to change the indicator's color. Okay? So, let's say we used phenolphthalein. All right, and for whatever reason, phenolphthalein is going to change color at the end of this reaction. Okay, so what's the concentration of A? Okay, guys, can you work on that one? What's the concentration of A?